Okay, so welcome to this new lecture on mechanical vibrations. And before moving towards today's lecture, I would like to actually bring your attention to the one of the problems that we solved in the previous lectures, and this was about the stability analysis of a structure given here, and we have actually included the weight of this disk, as you can see here. I have included the weight of this disk and also the weight of this rod in my analysis, and this is because it's a vertical system. The simple answer to this question is that because it's a vertical system and the effect of gravity therefore is included in this analysis. And moreover, if you are solving or analyzing the stability of a structure, and especially if it's a vertical structure, you need to include the gravity. Okay, so if you compare this problem with the last problem that we did in this lecture, uh, this one. Okay, so you can see that this is a horizontal system, and therefore while I was solving this problem, I never considered the effect of gravity, and moreover this was not related to the stability analysis. So when you are solving vibration problems, you have to keep this in mind, that you have to include the effect of gravity if you are dealing with a vertical system. And so we're going to move towards our new lecture. And if you remember, we did some lecture on forced vibrations and damped forced vibration last time. So I would like to begin this lecture by solving few problems from the previous topic, and then we're going to move on uh, to study the next topic of chapter number 3. Now this problem says that a rotating machine is to be placed at the free end of a cantilever beam which has a length of 1.2 meters and flexural stiffness of 20808 Newton meter square. Flexural stiffness is, by the way, the product of EI. The mass of the machine is 50 kilogram, and due to unbalanced rotor, the machine is found to generate a harmonic force given by this expression: Ft equals to 100 into cos 10 pi t. Neglecting the mass and damping effects of the beam, estimate the response of vibrations being produced. Also find the frequency ratio. So this is the diagram of the situation that is being given in this question. We have a cantilevered beam of length 1.2 meters and flexural stiffness given, and a machine is placed on the free end of this cantilever beam, which has some kind of an unbalance in it. And as the machine operates, it is found to generate this kind of a harmonic force. So this harmonic forcing function or excitation function is acting on the machine at the free end of the beam, and because of this there are some vibrations, and we need to find the response of these vibrations. So we realize that it is the case of forced undamped vibrations, therefore the response can be given by this expression 1. So we all know that if we are dealing with an undamped forced vibration in which the excitation function is harmonic, so therefore the response function will also be harmonic with the same frequency but a different amplitude x, and this x is found to be uh, in terms of equation number 2. And so this formula is valid for undamped forced vibration response. Now we need to find out the values of f naught, k, m, and omega square. So we can say that f naught is actually given, which is the magnitude of this harmonic function, that is 100 Newton. The mass is also specified, it is 50 kilograms. The the frequency of excitation is 10 pi radian per second. Okay, and the stiffness of this cantilevered beam can be found from its formula, that is 3ei over L cube. So values are given, and we can find the value of stiffness for this structure. Then substitute all the result in equation number 2, and we will going to get the amplitude of the vibration, that is 7.56 millimeters. So this means that the response is 7.562 cos 10 pi t, and this negative sign indicates that the response is 180 degree out of phase compared to the input excitation. Secondly, we need to find the frequency ratio, that is R, and R is equal to omega over omega n. So this omega is the excitation frequency, and this is the natural frequency, and we know that the natural frequency can be written as under root k by m. We have already found the value of k, 36125. M is given to be 50 kilograms. We can get the value of natural frequency, that is 26.879 radian per second. Omega is already specified in the harmonic function, 10 pi. So omega will be 10 pi radian per second, and therefore R comes out to be 1.168. So we see that R is indeed greater than 1, and if R is greater than 1, then the amplitude of the vibration response will be negative, which means that it will be 180 degree out of phase. So this result is satisfied. We move on to the second problem. An 82 kilogram machine tool is mounted on an elastic foundation. An experiment is run to determine the stiffness and damping properties of the foundation. When the tool is excited with a harmonic force of 8000 Newton at a variety of frequencies, the maximum steady state amplitude was recorded to be 4.1 millimeters at a frequency of 40 Hz. So estimate the stiffness and damping of the foundation. Now you have to uh, focus on a point that they have recorded a maximum steady state amplitude. Okay, and they are asking you to estimate, rather calculate, the stiffness, which is k, for this foundation, and the damping ratio, which is zeta. So you have to calculate it, estimate it using some calculations. Okay, the frequency at which the maximum amplitude is recorded is given to be 40 hertz, and the maximum amplitude is 4.1 millimeters. And you all know that this is the case of a damped forced vibration, and maximum amplitude in case of damped forced vibration only applies to the case under damped cases. Okay, where zeta has to be greater than 0 but less than 1 upon under root 2, because we have seen for when we were dealing with the plot of magnification factors versus the frequency ratio, we have seen that if zeta is equal to 1 upon under root 2, or any value that is greater than this value, uh, the curves were not plotted, they were not having any maximum. So therefore, whatever zeta we will going to find here in this problem, it must satisfy this condition. And so this is the diagram of what is mentioned in the in the problem. We have a machine tool, and it is placed on a foundation, and this foundation has some stiffness and some damping. Okay, so we are required to find out the stiffness and damping of this foundation. And this machine tool, when it is operating, okay, it was actually operated at different frequencies, and when it reaches this frequency of 40 hertz, the maximum amplitude of 4.1 millimeter was recorded. So in case of underdamped forced vibration response, we have two formulas that actually relates with the maximum amplitude of vibration. The first one is the maximum value of the magnification ratio or magnification factor, and that is equal to 1 upon 2 zeta under root 1 minus zeta square. And you all know that this amplitude, this magnification factor is actually the ratio of maximum amplitude divided by the static deflection of the foundation, static deflection of the foundation. And the second formula that is valid for the case of underdamped force vibration response related with the maximum amplitude is this value of R, the frequency ratio. So at this value of R, the maximum value of the magnification factor is given as 1 upon 2 zeta under root 1 minus zeta square. So we have these two equations, and in combination with these two equations, what we can do is that we can write down the very famous equation of the natural frequency, which is omega n equals to under root k by m. Let it be equation number 3. And we also know that delta st, that is the static deflection, is equal to the magnitude of the force applied upon the stiffness of the system, that is k. So this is equation 4. Now what we need to do is that we need to find the value of zeta, and then if we can find the value of zeta, we can also find the value of k. So substitute the values of static deflection, delta st and k. Okay, first of all, just look at the expressions of delta st and k. Delta st is given by equation 4, and k can be obtained in terms of omega n from equation 3. So substitute the values of delta st and k from 4 and 3 respectively in equation number 1. Equation number 1 is this. So in this equation, we substitute the value of delta st, that is f naught upon k, and then the value of k will be substituted from equation number 3 in terms of omega n. So when we're going to do this, we're going to end up with an equation that involves the value of omega n. At that instant, we have to find the value of omega n from equation number 2 and substitute in equation 1 to get an expression for zeta as follows. So what we will do is that we will going to we're going to find the value of omega n from this equation number 2. Okay, that will be of course omega upon 1 under root 1 minus 2 zeta square. So from this equation, we're going to again substitute the value of omega n in equation 1, and finally we will get rid of all the unknowns, and we're going to get the expression of zeta in terms of all the known variables of our problem, that is x max, which is 4.1 millimeters, m, the mass of the machine, is 82 kilograms, omega is also given, okay, so it is 40 hertz, f naught is given, that is 8000 Newton. So the only unknown in this expression is zeta. Okay, so every other variable is known. So by solving this expression for zeta, we end up with this equation. Okay, it is a quadratic equation. You can always assume that z equals to zeta square, so that this equation will be converted into a quadratic equation with the power 2, degree 2. So it will be z square minus z plus 0.03107. And since this is a quadratic equation, you can find the values of z1 and z2 by using the quadratic formula. So here you see that a is equal to 1, b is equal to minus 1, and c is equal to 0.03107. And from this equation, you get the value of z1 as 0.967. So z1, when z1 is 0.967, then zeta will be under root z1, zeta 1 will be under root z1, and you get the value of 0.983. But you notice that zeta 1 comes out to be greater than this value of 1 upon under root 2. So we will just going to ignore this value, and we have to find now zeta 2, z2 actually. So z2 comes out to be 0.033, which gives again from this expression gives us a value of zeta 2, that is 0.1816. And so this value is lower than this 1 upon under root 2. So we're going to select this value for zeta for this problem, and zeta comes out to be 0.1816, and this is your answer 1. So again, what we can do is that now, since we already know this value of zeta 0.1816, we can again go back to equation number 1. Okay, we know this value zeta now, so we can substitute delta st as f naught upon k and calculate the value of k from this equation 1. So using delta st from 4 in equation 1, we can find the value of the second unknown of our problem, that is k. And putting all the values here and solving for k gives us 5.464 meganewton per meter. So this is our answer number 2. So we have designed the stiffness and damping, or we have rather calculated the stiffness and unknown damping and unknown stiffness of our foundation by performing this simple experiment. That is, we tried to operate this machine at different frequencies and put some vibration sensor on it. So at a frequency of 40 hertz, this system gave us a maximum amplitude of 4.1 millimeters. Okay, and so because it gave us some maximum value, therefore we use these formulas and we have estimated the damping and stiffness in it. So this is the new topic of chapter number 3, uh, vibration isolation. And vibration isolation is a very, very important uh, situation in vibration engineering. So let us define this terminology of vibration isolation. Vibration isolation means to design isolators, that is springs and dampers. So isolators in vibration engineering means spring plus dampers. So this is a new word given to the collection of springs and dampers. Isolators, they are actually behaving as vibration isolators. So vibration isolation means to design isolators, that is springs and or dampers, in such a way that an object or equipment can be protected from the harmful effects of vibrations. And the harmful effects of vibration are actually large amplitudes, so we have to avoid large amplitudes of vibration, and transmission of dynamic forces. So vibration isolation means that you have to save your equipment, your device, your machine from large amplitudes of vibrations and dynamic forces, because all of these can cause damage to the structure. And there can be many different shapes and sizes of these isolators found in the real world. For example, here you can see an undamped spring mount. Okay, it's so springs, coil springs or springs can behave as vibration isolators, stiffness elements. And this is an undamped spring mount that can be directly attached between the device and the foundation. Here a pneumatic rubber mount is given, so some air pressure can enter and can be taken out as required from this pneumatic mount. Then this is a sort of a enclosure, a sophisticated kind of an enclosure device that contains damped springs. So damped springs means that there might be some dampers, hydraulic dampers, oil based dampers in you know arranged in parallel with these springs within this enclosure, this casing. And here you can see some pneumatic rubber mounts placed here between this machine and its foundation, the floor. So all these kind of machines that are dynamic, they need vibration isolation. Okay, so the prime objective of a vibration isolator is to protect your device, your machine, from harmful effects of vibration. So this means that, for example, if you consider this machine as a structure, okay, and it is maybe vibrating with some amplitude during its function, and so this vibration is being transmitted to the floor, or maybe towards the foundation on which this machine is installed, and you will going to protect that foundation. Okay, So you want lesser and lesser vibration to be transmitted to the floor. Uh, the other way around, the other story could be that if the nearby machines are vibrating vigorously and they are transmitting vibration to the foundation of this machine, and from the foundation of this machine the vibrations can enter into this equipment and cause some hazards. So you have to protect both the ways. So in this regard, we first consider the topic of harmonic bass excitation. Bass excitation means that the base or the support on which your equipment is mounted will be excited, but it will be excited harmonically, only harmonically. Okay. So the vibrations are being transmitted to the structure through the excitation of the base or the support. And the real world examples of the situation could be vehicle vibrations due to rough road, earthquake, sensor attachments, camera attached to a fighter jet or a vehicle, and a machine placed on a floor that is vibrating. All these cases are can be the example of base excitation. So what will going to happen is that displacement and force both will be transmitted through base excitation. So when the base or the support of a apparatus or an equipment is in vibration, it will going to transmit both the quantities, displacement and force. And in order to find out the magnitude, we should know the magnitude of force that is being transmitted to the device and the magnitude of displacement that is being transmitted. So both the magnitudes are important for us as vibration engineers. And so in this topic we will going to explore the dynamics of this kind of a behavior, and we're going to find out the expressions by which we can have some knowledge on how much displacement is being transferred, or what are the amplitudes of the displacement being transferred, and what are the amplitudes of forces that are being transferred. So here we have a inertia element which can represent a machine or an equipment or an apparatus, anything, and it is connected to its base through these isolators. So as I told you that the combination of spring and damper is known as an isolator. So the isolator is mounted here with your mass, with the inertia element, and they are mounted here with the support or with the base. And what is going on is that this base is actually vibrating with this kind of a input excitation. So this is harmonic input excitation, y sine omega t. So this kind of a harmonic function is applied on this base. So because of this, the vibrations are transmitted to this machine, the displacements are transmitted to this machine, and this machine also starts to vibrate. Okay. So since both the ends of these isolators are actually moving relative to each other, so therefore we will going to take the net effect, that is x minus y, with reference to this displacement x. Okay, the net effect is x minus y and x dot minus y dot. So this motion is positive upward, therefore the recovering forces of the damper and spring will going to act downward, and that is why we have shown on this free body diagram downward motion of spring, the downward motion of the damper with the net relative displacement x minus y, and relative velocity is x dot minus y dot. So we need to apply the Newton's second law in translation in the y direction, that is submission F in the y direction equals to mx double dot, and we have two forces, recovering forces, that is damping and this spring stiffness. Okay, so we write them down here, and then we will going to open these brackets and simplify our equation, and we will going to get this equation number 1. So here we have y and y dot, and we know that y can be written like this: y sine omega t. So we need to differentiate this with respect to time to get the value of y dot, which is capital Y omega cos omega t. So we substitute these two results in equation number 1, and we get this kind of an expression number 2. Now, if you look this equation number 2 closely, you will notice something. On the right hand side, we have sum of two harmonic motions. Okay, one harmonic motion with this amplitude, the other harmonic motion with this amplitude, and so this represents a formula of sine alpha cos alpha sine beta, which is sine alpha plus beta. So we can write down this right hand side in a compact form as a sine omega t plus alpha. uh, so you should now remember from chapter number 1 that this represents the resultant of two harmonic motions or sum of two harmonic motions. And when this is the case, we need to find the value of A and alpha. And for that, we have to recall this topic from chapter number 1. The resultant of two harmonic motions. We did this topic in chapter number 1, and we say that the resultant of these two harmonic motions can be written like this, where A can be found from this diagram that was having this formula, and alpha is this value, tangent inverse of this divided by this. Okay, so we have already gone through the this topic in chapter number 1. Therefore, in the present case, we have this equation of motion, and we know that the right hand side represents the sum of two harmonic motions, which can be written like this: a sine omega t plus alpha, and this a will then be equal to under root like this one. This a will be under root square of this and square of plus square of this. So it will be k square y square c square omega square y square, and so y square can be taken out of the radical sign, and we are left with under root k square plus c omega whole square. And so tangent alpha from this formula will be this value divided by this value. So alpha comes out to be tangent inverse of c omega upon k. So we can finally write this equation of base excitation like this. Okay, just putting the value of A, we just substitute the value of A, and we get this equation. Now if we compare this equation with this one, you can see that this again represents the equation of damped forced vibrations. Just in this case, F naught is given by this expression, capital Y under root k square plus c omega whole square. So we end up with an equation. We actually started with the base excitation, where we claimed that this base was moving harmonically with this function applied at the base. Just simply carried out the Newton's second law of motion in the y direction, and we end up writing this kind of a equation. And so we realize that this is the sum of two harmonic motions, so therefore can be written like this. And once we did this, we recalled what we did in chapter number 1 to find out the value of A and alpha, and from that we just saw that it is nothing but again the equation of damped forced vibration. So we know that for damped forced vibrations, the response can be written like this. The particular response especially can be written like this. So since this is harmonic, the response will also be harmonic. Okay, but since damping is involved, there will be some delay, minus phi. Okay, and this is the amplitude of vibration of our inertia element because of the base excitation. So this x is very important for us, and we know that for damped force vibrations, this x can be written like this. We just did this in the previous lecture, and phi can be written like this: tangent inverse of this value upon this value. So now it will be important for us to represent uh, this x in terms of magnification factor or in terms of a dimensionless quantity. So what we will do is that we will going to insert in this expression the value of f naught, and we know that in our base excitation case we have just found out that f naught is equal to this value. So we're going to put this f naught here in this equation. Okay, that is this value, and then we can write down, we can bring this y in the denominator, and it will be then x upon y